So, hi everyone, I'm Sydney Vanda, and I'm also here with John Salinas, my coworker. We're going to be talking about ZFS validation and quality assurance. So, the purpose behind this presentation is truly to focus on bringing Linux up to speed with regard to ZFS validation, both with our team's testing efforts as well as the community's. So, with this, I'm going to be discussing the ZFS test suite, and with that, the real disk support that our team has been working on and currently added to that. As well as that, I'm going to address some standardization areas that I've noticed within the test suite that needs to be addressed. Next, I'm going to be talking about the performance regression test suite. And with that, I'm going to talk about how our team is currently using this performance regression test suite to validate our current features as well as compressed arc features. And I'm going to give another overview on that for anybody that's unfamiliar. And next, John Salinas is going to wrap up. He's going to dive into the ZFS test suite a little bit more, and he's going to talk about how we're using that to inject failures and different methods for that, and also how we're validating other features with that. And finally, at the end, we would love to get a community response on not only our work, but also how we can all collaborate to make the ZFS test suite and the performance regression test suite, tools that enhanced tools that we can actually use for the better, at least within Linux. So earlier this year, ZFS on Linux landed the ZFS test suite from Salinas that Delphix was using for Illumos development. So for those unfamiliar with the ZFS test suite, it is a series of command line interface regression tests that are aimed at testing the production software as opposed to other tools like ZTest, which mainly just focus on testing the core algorithms. So there's still a considerable amount of work for integrating the ZFS test suite into ZFS on Linux. Currently there are, I think, about 650 tests running with still a good percentage of tests still disabled within this test suite. I think there were just under 1,000 tests in the original Delphix test suite. I'm not sure about the current state of that. But anyway, and a lot of these tests that are disabled, some of them actually do work, some of them require some minor Linux equivalence fixes, and some of them need some more investigation into why they actually do not work within Linux. And John's going to be discussing some failures a little bit later, more in detail. So the tests are basically, they're generally small, not too complex. They're all grouped together with similar tests. They test all the positive and negative test cases for a single command, such as all the zpool create tests. And within all of these test groups, they have independent cleanup and setup scripts. There are some default methods for cleanup and setup. However, those are rarely used, and I'm going to discuss that a little bit later when I discuss the need for standardization within the test suite. So here's just a little overview of the ZFS test suite. So right now there's 103 test groups, and a little bit over a quarter of these enabled test groups require disk partitioning. So right now the test suite, you basically have 3 defined devices, and then those devices are partitioned as needed if you need more devices for certain tests that you're running. There's 650 running tests, like I said previously, and 213 disabled tests. The original port of the ZFS test suite into ZFS on Linux only supported loopback devices. So in order for this test suite to actually be useful for our team as well as everyone else, real disks needed to be used. So our team pushed to get real device support patch landed into ZFS on Linux master earlier this month. So basically, partitioning was previously done by setting a slice prefix variable to P by default. But in order for it to handle anything else besides loopback devices, basically functionality needed to be added to determine the device directory and the naming of the device within Linux. And this is all defined within the disks variable that you basically set within the run script. So, and another thing to note is that basically there will need to be a push to move to persistent naming, because right now it is non-persistent naming path, such as dev SDA, but this will need to be moved to actual persistent naming for tests such as what Don was speaking of earlier, such as the fault management tests. And so parted partitioning is actually used right now for this patch, as opposed to other partition conventions such as kpartex. And this might, just for simplicity purposes, and this might cause some issues for distributions like Ubuntu where kpartex is enabled by default, and that actually might have to be disabled temporarily to actually have the test suite run properly. Another thing to note is that multipath devices currently have less capability within ZFS. So this was noticed by basically a Z-pool cannot be created on a multipath partition device. So this caused problems for tests that had size constraints requiring that required an entire device to be used and not just a partition for some tests, and also for the default cleanup method. So the default cleanup method currently involves basically creating a new pool on an entire multipath or an entire partition device, and then once that pool is destroyed, so are all the partitions of the device. So it's like a nice cleanup method, but that's not going to work with multipath devices. So they needed to be handled differently, and currently they're just all of the partitions have to be deleted until something better is thought up for that. But it works fine for SD devices and of course loopback. So while implementing a change like the real device partitioning that basically incorporated the entire test suite, some things were noticed about some areas of standardization in the suite that need to be addressed and brought up to the community. So the use of, or actually lack thereof rather, of configuration files within different test groups. So there are some tests that have configuration files, however, a great majority of them do not. And the configurations file basically have some important variables that are basically used throughout, and there's a lot of repetition, and this is also where the slice prefix variable for partitions and also the device directory gets set. And this functionality can actually be abstracted even higher, but right now there wasn't really a good area to actually abstract this wasn't seen within how the current framework of the test actually, the test suite actually is. So it's just kind of an awkward area, and right now there's just a lot of repetition, and basically it all has to be within all of the setup scripts. Some early failures and asserts for commands not present. So basically within the setup script, there should be some sort of asserts for commands not added to the system. Because right now, basically you could have the entire test suite run. So 2 hours later, when you have 90% failures, you basically find out that you didn't have the parted command or something dumb like that. And default cleanup and setup scripts. So like I was mentioning earlier, basically very few tests actually use the default setup and cleanup methods. There should be some sort of standard for that. I mean, when you actually make a change within the entire suite, it makes it a little bit way more difficult actually, because you're dealing with different tests that have a different cleanup for everything versus when you could just have something when they all call the same function. So there should be some more defaults for that, maybe with some different, whether you include partitions or you don't include partitions, or some other constraints, so that can be some more, that can be easily defined there. So the performance regression test suite, this was pulled into OpenZFS from Delphix as a part of the compressed arc feature, and then these tests were actually separated out of this patch and ported into ZFS on Linux by my colleague Don Brady a couple months ago. So a little overview of the performance regression test suite. It's actually a directory of performance tests that's used by running the exact same test script as the ZFS test script. But all you have to do is include the -r option and the performance regression run file. And all of the tests within the performance directory are currently enabled. However, this patch was not complete, and some future work that needs to be for ZFS on Linux is that we need some sort of tools to easily visualize the difference between different output of runs, so you can see exactly the performance impact that you have, as well as there's additional regression tests from Delphix, as well as functionality that is yet to be ported into ZFS on Linux. So here's an example of how my team is currently using the performance regression test suite to validate features such as compressed arc performance. So the results displayed here are from the log file summary from the end of each run, and it shows the bandwidth and the IOPS. So here's an example of synchronous read and write bandwidth. So the baseline runs with SD devices, and it's compared to the performance results of the compressed ARC patch, as well as the ARC refactoring and the compressed send receive patches. So something to note is that ABD, the ARC buffer data, is not included in this. But compressed ARC itself was a major rewrite, so tests like this can help us easily show that there's no significant performance regression, and there's even some small improvement in some areas. And something else to note as well is that these tests currently stop at 1 meg I/O, and we're not going to really see the benefit of compressed ARC unless this is pushed way beyond that, from 2 to 16 meg. So again, here are some initial results for random read and write. So these graphs generated, these graphs again are, oh, I'm sorry, oh, yeah. These graphs are generated separately to quickly see the performance impact, and some of these tests might not actually even be appropriate for compression analysis. This is just more so to bring up the point that there needs to be some sort of script to consume all of this performance data and display the comparison results easily to actually make this performance regression test suite useful. And I think that there might be some sort of capability within that in Delphix or something else, so getting that within ZFS on Linux is going to be key. So again, the results showed previously were from log files, which give the IOPS, the read-write I/O, and the bandwidth averages. But there's also a significantly many more statistics generated from IOStat, VMstat, and zpool IOStat, as well as MPstat. So there's just, here's a couple few snippets of actually a sequential write, 128K I/O, 128 thread tests. So some future improvement that at least our team is going to need to address is that different pools are going to need to be added, including the DRAID pool, into these tests. Larger IOs are going to need to be used, extending beyond 1 meg, as well as seen in the IOStat. I don't know if you can see that, the results, but the request sizes are actually pretty small, and our team is going to need to push this to at least 2 meg to be suitable for HPC workloads. And so basically, to wrap up the first little part of this presentation is that ZFS on Linux landed the real device support patch. So now the ZFS test suite, as well as the performance regression test suite, can be used with real disks, which is a good thing. Also, some process of standardization across testing groups within the ZFS test suite should be brought to light at some point and addressed. And also, the performance regression test suite, which was recently ported by Dawn into ZFS on Linux, is runnable on Linux. More work is needed, however, and adding capability for larger IOs and some sort of ability to easily see the performance impact. And now I'm going to hand off to Dawn for the rest of.
Okay, thank you for having us here to talk about testing. I know it's not the most exciting topic, but as all of you wonderful people are making new features, we have the opportunity to introduce new instability. So I'm going to talk a little bit about how we've been using ZTS to hopefully avoid some of the problems that could come about. We have basically 3 stages that we're using right now. So as our developers check in code, it comes into Garrett, hopefully, so we can do code reviews. Jenkins goes ahead and builds it and then produces some artifacts. So we have a process that watches over Jenkins artifacts called auto-test. And then the second phase here is our CI, our continuous integration testing. So in this phase, we basically have a basic acceptance test that runs. That's things like the zconfig. I think we still have some of the old Z faults. Just really simple stuff to make sure, hey, can we make a pool? Is the really simple stuff there? Z loop ones for around 20 minutes. And then we do have a ZTS quick that we do. So all the basic tests that are flaky or we don't have in this is just a core of tests that runs in about 30 minutes. And we also have some XFS tests. So when we run this, when a developer checks in code, we want them to know that basically the basic stuff works. We want to give them feedback very quickly. And we want 100% of this to pass, or the testing tools won't give them the ability to merge their code. There's a second phase, we have two. So we do a weekly build. On Thursday night, we drop a build. And this is a little more extensive, right? So this runs from Thursday night all the way to Monday morning. So we make use of the Luster test. So Luster has a test framework called Oster that it runs. We run all of the ZFS review 1 and 2 on there. So Luster is a great way to consume and to use ZFS. So we use the Luster test. So ZTS is really good about testing commands. You know, does this command option work? You know, does this other command option work? Luster isn't so great about testing all the various command options, but it does have fairly interesting cases in there for, well, will this type of I/O work? Or if we do this weird use case that some customers brought to us, will that work? So this gives us a little more coverage. We run Z-loop continuously, and we run all of the ZTS leads, including the flaky tests, and we run them over and over. So I think in the course of this, each test runs about 20 sometimes. We have FSX that runs, ZFS stressed Trinity that does some fuzz testing of system calls, and we just kind of let that stuff brew in the background. We're working on getting the performance testing stuff running on a real JBOD. Some of this stuff runs in VM, some of this stuff runs on real hardware. So this gives us the way to put a bunch of patches together and say, okay, so this week's of work, does it actually hold together? Is it stable or not? Because it's hard to do that on one check-in, right? Because we don't want the developer to have to wait 3 days to know if their stuff is stable. So we have to give them results quickly, so we can use ZTS in a quick or in a long context. So what do we do when ZTS fails, right? So that never happens. So in at least ZFS on Linux, we only have right now one case that seems to fail all the time. So if you run ZTS on Linux, RAID Z02 positive pretty much always fails, and it will always continue to fail until we do something about it. So we like solid failures, though, because they're easy to track down. So the problem is when people submit code, it's great that they submit tests, but when the tests don't pass, that is a concern. So in this case, when you go ahead and actually look at why it's failing, the code has two options, a -cap S and a -T. The -T is supposed to be seconds. It's set to 300 by default. On our test systems, which are fairly modern Haswell systems, 72 cores, 64 gigs of RAM, the 300 seconds takes about 23 to 25 minutes. So there's some timing issues there. And actually, if you go read the comments in the test case, it says, oh, by the way, this may run a lot longer than expected. So seconds is something that you probably shouldn't take too literally in this test. So in this case, it's not actually a test failure, right? It's just that the seconds, the unit of time measurement isn't accurate, right? So we just set it to -T40, and voila, RAID Z2 positive passes all the time now. So this is just a case of a solid failure. We find out why is it failing, go ahead and fix it. The harder ones are the intermittent failures, right? So I don't have any data. I've never looked at the other releases, but in ZFS on Linux, it's pretty common that we get a fair amount of intermittent failures. The upgrade tests in particular, compress, uncompress, send, receive is another one. These fail fairly regularly, right? So you'll submit code. The problem is we don't track these in any way. So if you submit code to ZFS on Linux and the builders tell you, hey, something fails, it's difficult to say, oh, this failed because of a known intermittent failure. So internally, we're tracking all these failures now, so we can go back and say, oh, okay, Dawn broke the code with a new bug in this test, or oh no, that's a bug we've always known about, so it's not a big deal. So we're trying to figure out then why do these tests fail. And basically, we have to enable the debug information. Sometimes it's just a -X. Go see why it's failing. I'll get into the failures and correcting those in a little bit more, but then we decide, is it worth keeping or not? So basically, for our quick tests, we don't want any flaky tests because we want all those to pass. So we have to fix those tests before we put them back in our quick test. Okay, I'm going to use an example of online, offline. So when I started and I was going to get a test going for DRAID, I looked at online and offline and said, that's something that I want. I want to be able to take a DRAID pool. I want to have I/O going to it. I want to fail a drive. I want to bring it back online. I want to fail a different drive. So online, offline did probably 80% of what I wanted to do out of the box. The only problem is online, offline fails every time you run it on Linux. So the current code starts a file truncate for I/O, and then it offlines and onlines one of the mirrors. The problem is that the truncate option is specific to something that is not Linux, right? So it's never going to work on Linux. And even if it did work on Linux, which was the first thing I tried, I just fixed the options, is truncate returns really quickly on Linux. So on whatever system this was originally written for, apparently truncate was very slow, right? So they used truncate to start I/O and do all these pull operations, and then it would go and kill the truncate process. Well, the test was failing on Linux because when it goes to do the kill, it's a bare naked kill. The kill fails because the truncate process has finished long before they tried to kill it. So it's just not a good deal. So here's a really hacky example of how we might fix this, right? So on the one side, this side over here, we have the original version where we just do the file truncate. No -F option exists on Linux, so that's never going to work. But the kill really bothers me in this, right? So this is not a good idea. One, we're not checking to see if a process is there, but I mean, what if we kill it and nothing happens, or the kill hangs? It's not super good. So I've, just as a temporary measure, I've wrapped the kill in something else so that at least it's not going to make the test fail. And instead of using file truncate, I've switched to DD. As I thought about this more later, probably this isn't a really good way either, because if we're just doing random I/O, for me as a tester, I want to know what I've written out is actually valid. So this is really hard to validate too. So that's another concern we have with this one. So these are temporary solutions. I'm going to talk a little bit more in 2 slides about why I think they're temporary. But here's an example using Sydney's real disk patch that we've got I can't actually read that, but we've got 3 disk devices up there. You can see one of them has been offline in the first example, and then the test go ahead and brings it online. And now you can see that we have the online, offline 0, 1, 2, 3 are now working on Linux. So you've asked, okay, that's fine. Why haven't you submitted this code upline? Well, there's another issue that I want to solve, and then we'll get to the why haven't we uplined any of this stuff yet. As I've been going through these tests, the other thing that's concerning to me is validation, right? So it's one thing for me to issue a command, you know, zpool create, let's see something happen. It's another if I don't actually ever validate what that command did, which is generally the case in the ZFS test suite. So the case of ZFS create 003, there is a test to say, okay, yes, the command executed and it didn't return an error. But that doesn't give me assurance as a tester that I trust what that command has done, right? So there's no verification. In this case, it sets a bunch of different block sizes, and I want to actually know, are those block sizes actually what they are set? So on Linux, I don't know if this is portable, it probably isn't, but on Linux, in this example, we've gone ahead and we have a second block of code that exists, and basically we iterate through some different block sizes, and then we use ls block on that zpool, I think it's a zfall, and we get the block size that's been created, and we can say, yes, okay, so we've done something to validate. We don't want to just run a command and assume because the command didn't, you know, horribly fail or the system panicked that it worked. We need some way to validate that this actually did what we wanted it to do. Test must not assume because the command worked that it worked as expected. Our goal is not just can we run a command, our goal is ZFS doing something sane? Is it doing what is expected? We want to move beyond just as the command run to are we properly validating this in the right way? So future considerations. First thing, right now, at least on Linux, I can only run on 3 disks. Very complicated to make any sort of real-world setup on 3 disks, right? This is a problem that we have to be able to move beyond. To go back to the question of why haven't you uplined these fixes, right? This is the conundrum that I've faced as I've thought about this. As I look in the test codes, there's more and more of these huge blocks of if Linux, do this bizarre thing. If not Linux, then do this other bizarre thing, right? So I want test codes to be test codes. I don't want to be worrying about what platform am I on, what am I supposed to be doing. In the test code, I want to be worried about testing something. And since I have the test routines, I think we need to move away from these bizarre blocks of if, else, platform to different routine names. So instead of, in the first example we showed, instead of doing, you know, if Linux dd, if not file truncate, I should just call start IO load, right? That should do something. And inside of that routine that's abstracted in a level above the test case, everyone can use it, and we can make it sane for whatever platforms, right? Because I don't know what's best for each platform, but you guys can help me with that, right? Instead of, a bare kill, we should have a process, a routine that goes out there and it says, okay, is the process there? If I try to kill it, is it actually going to die? Because we have this happen with ZTS, right? Z-pull is hung. It's unkillable. Every test case in ZTS will go and try to remove that pull, and every one will fail, right? It's not sane. We can't do that. So the test case doesn't need to worry about what platform it's on. The test case needs to worry about, is ZFS working, right? So that's what we want to move towards. So basically what we're suggesting, instead of my ugly fixes for routines, in the hackathon, what we'd like to do is put those into some routines, abstract them in the level above, and if you guys think that's a good idea, then we can upstream that code. Test runner is another one. For me, it's very difficult as I'm running it, because I run ZTS a lot, to know where I am, right? So it's got a million tests, okay, 600 and some for us. But I want it to say, I am on test 5 of 500, so I know if I can go get a cup of coffee, or if I should sit here and wait for it. The stopping on error is a big one, right? So all the time, especially if we've hit an assert or something really nasty has happened, I know that every test case after that's going to fail, right? But everyone is going to try. So we need some way in the test runner code to say, hey, I give up. It's not worth trying to run past this point. And if we can dump out some of this stuff and say, hey, we need all the tests that have failed, just go look over here. Because you get this big, long output, right? And you've got to search through or have a bunch of grep post-processing. Let's provide some output so people can tell what's actually failed and what hasn't. So error injection. This is something that someone brought up here earlier. ZTS seems like the perfect place for error injection, right? So I'm doing an offline-online test. That test is doing it in the safest, best case way possible. But we want ZFS to work in a worst case world, not just in a best case world. So am I online and offline? I need errors, right? I can't just online and offline stuff that I know is going to work. So Z-inject is a great way to do that. There's this great tool here. Here's an example of injecting a read error in a pool. I can start some reads with DD or something simple and check the status again. So when I'm offline and onlining, I need errors in there. DM setup for Linux, SCSI debug for Linux. That's another great way where I can create error regions in a disk where I can say, okay, if I run over this, I know I'm going to get 10 EIO errors or 10 checksum errors, right? It gives us a programmatic way to create errors. I can remove devices, all that sort of stuff. So our summary, what do we want to do? We want to improve ZTS by correcting issues specifically on the ZFS on Linux. We want to correct issues so that we have more tests running, more coverage. We want to know that when we're checking in new features, we're not breaking old ones. We want to improve ZTS by adding verification steps. We don't just want to know, did the command run? We want to verify, yes, there's some way that we know that it actually did something useful. We want to improve ZTS by abstracting routines, actions out of tests like start IO, kill process, especially things that are platform dependent. We want those to be outside of the test. And we want to improve ZTS by adding error injection, right? We want you guys to be looking for worst case scenarios when you write tests, not best case scenarios. And when you guys check in code, right, there should be tests. It would be weird to create this great new feature and not have any way to test it, right? That's wrong. Of course, I'm a test engineer, so I'd say that. But we want ways to validate, yes, your great new feature works, and here's how you can demonstrate it works, right? And then as I look at that, I can say, oh, but what if I tweak this? It's not going to work anymore, right? So then there's a better back and forth so we can find more bugs before customers do. So I think that's it. So we'll work on this on the hackathon, but if you have any feedback for us or questions for us now, I guess is the time. But we would especially like to know if you're on board with our idea of taking the if, else, Linux stuff out of tests and abstracting that into routines. So we'd love to hear from you on that one. Yeah, go ahead. Okay. 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 Yeah, that would be great for those people online. Mr. Kinney was just saying that he agreed with abstracting routines, and he's actually addressed some of these things in, is it Delphix or in Delphix? So we'll look at some of those things tomorrow and go from there. So, any other questions or comments? What's that? Z-loop is just a wrapper that folks put around Z-test because Z-test doesn't run very long before hitting some sort of error. So I think the longest I've been able to run Z-test on Linux is probably about 4 days, maybe 5. And I filed a number of bugs, and no one has ever looked at them. So they've just kind of sat there and languished in sadness and sorrow. But to get around that, Z-loop is a script that some wonderful person wrote. So basically, instead of running one long Z-test, you run a short Z-test with different options. So you're getting a little more coverage in that you're getting different options, you know, all the options you can give. So you're getting a little more coverage that way. The unfortunate part is you're getting less coverage in the length of the run. So we may try to circle back around to the Z-test stability issues on Linux at some point, but basically it fails, right? And one thread of 1,000 is hung up somewhere, and tracking that down is quite tricky. So. Okay. Right. Yeah, that's a really good idea, adding a seed to Z-test and having a simplified Z-test. So for some of these things, we could at least figure out why. So, yeah. Did you have a comment?
As a follow-up to the seed, did you mention fuzzing earlier? And if so, how do you identify the dimensions and the parameters for the clusters?
Yeah, that's just for file system calls. So Trinity is just an external one. So. Oh, yes, the question was about fuzzing and how we do that, and I should have been more explicit. The fuzzing is for file system calls. We haven't done any fuzz testing just on general ZFS options or I/O testing. So, yeah, Trinity is the name of that tool that does that for Linux. So. There was one question I had for hopefully that someone that knows. I noticed in the test suite, right, so there's options for functional tests, which is where we're kind of living. Don and Sydney have started adding the stress test, and we hope to add more profiles to FIO for that. But there's also, or for the performance test, but there's also a stress directory, which is empty on Linux. Are there stress tests that exist? And future work? Okay. So maybe Linux can help with some of that. So Lustre has some, some things that I thought maybe we could pull over for a short, easy solution. But yeah, okay. All right. Thank you much.